So for our last talk, we're going to stick with the theme of color in diamond, and this will be given by my colleague, Dr. Mike Breeding.
Hello, everyone. Sergey showed us some beautiful pictures of colored diamonds there, and there have been several others earlier in presentations. As I've sat through the presentations, I've kind of been thinking, as scientists, I think sometimes we forget to explain exactly where the color is coming from, why it's there, and how we know what's causing it. And so I'm hoping that as you go away today that you'll have a little better idea of that after my talk. So unfortunately, my colored diamonds don't move quite so elegantly as the previous ones, but you get an idea that diamond spans pretty much the entire rainbow. And as we go through here, you always start a colored diamond talk with a colorless diamond, otherwise it just doesn't work. And we've heard all these great properties about diamonds, and this is about the best term I could come up with. Diamond has to be the most multifaceted material on the planet. It has such unique properties, yet it's composed entirely of a single element, carbon. And those carbons are not really that complicated. They're in tetrahedral arrangements, bonded to 4 other atoms. We all know it grows naturally, or we've seen it grown in a laboratory quite well these days with technological advances. But when you look at diamonds like this, these are some of Evan's Clipper diamonds. I think this is what most people would see and they would think of as described as perfect. They're definitely rare. They're extremely rare. And you look at these, they're clean, they're clear, they're type 2A. They're about as perfect as diamond can get. Or maybe after you facet them, when they get D-color flawless grades, you could probably believe that even more. Well, I don't want to be a natural elitist. These lab-grown diamonds are equally as beautiful and equally as pure, and in some cases even more so, reasonably perfect, definitely not rare. But that led me earlier to start thinking about what does it mean when we say perfect? And as any good scientist would do, I pulled up my phone and I Googled it. So, according to the Webster Dictionary, and this couldn't have come out more beautifully had I tried, perfect is defined as being entirely without fault or defect, flawless, and even better, the example is a perfect diamond. Well, you'd think I may trigger on the diamond part or the flawless, since I just showed you a D-flawless diamond, right? Actually, the part that I'm more focused on is this word, defect. And to spoil the whole title of the talk, there are no perfect diamonds, especially by Webster's Dictionary. No matter how pure, no matter how clean or perfect, all diamonds have defects in them. And that's not a bad thing, actually. I think you'll see by the end here. I want to give you some examples of how powerful defects, imperfections at the atomic scale can be in diamond. This is a very simplified carbon diamond lattice. All of these carbon atoms, this is a perfectly pure, perfect diamond. It's colorless, as you can see. If I do have some fun, though, in nature, and I use radiation and I knock out some of those carbon atoms and leave vacant areas, now the way this diamond interacts with light, or specifically these defects, they can cause intense colors like this green. And you just saw one in Dr. Cohen's treatment experiment, which involved radiation as well, the same premise. Well, that's fine and all, right? Well, let's start again. And what if rather than removing anything, I just simply kind of kink the lattice a little bit? In nature, when this happens, quite often you'll form these groups of vacancies. By themselves, they create green color, but in groups, they do something very different. They interact with light in a way that usually gives you a brown color. In fact, brown diamonds are probably the most common diamond discovered. And if you're a gemologist and you look at diamonds, you often see brown grain lines in diamonds. That's defining these bands of plastic deformation. In certain very unique cases, like a lot of the diamonds from the Argyle mine, these are configured just a little bit differently, admittedly in a way that we don't fully understand, to give you pink to red color. So subtle differences can have profound effects. All right, well, let's go back to our pure diamond. And instead of just working with what we've got, let's add some things. So if this diamond grows with nitrogen, you saw this in Dr. Wang's talk first thing this morning. This is a type 1b diamond, single isolated nitrogen atoms. Gives rise to a canary yellow type color. I don't have a picture of the bird, I apologize, but it's much more dramatic that way. But if instead of nitrogen we substitute boron, apparently 500-600 kilometers down in the earth, as we heard earlier, you get these nice blue colors. Many, many famous diamonds, and as you'll see at the end of the talk, they're not just famous, we'd all like to have some. All right, back to nitrogen. Boron doesn't really do that much more exciting beyond that. So with nitrogen though, there's a lot of complexity that comes out of such a simple carbon-based lattice. If you put a vacancy, knock a carbon atom out next to a nitrogen, you get a pink color, and it can go all the way up to red or orange. And yet again, Dr. Cohen showed us a nice example of what happens when you put a lot of nitrogen vacancy defects in a diamond. You can make a nice red color. All right, well, you know, we just made pink right there, and this seemed to be following a progression, right? We were getting more color, the more complex we get. Well, look what happened now. I put 2 nitrogen atoms beside each other, and then also 4 next to a vacancy, and now I've lost all my color. So it's not so simple, it's not so straightforward. This simple carbon-based lattice is a lot more complicated when you start adding defects. All right, well, let's keep going. We move those nitrogens apart and put a vacancy in between. We have a nitrogen vacancy, nitrogen center, or we have 3 nitrogens around a vacancy. Both of those produce fairly strong yellow color. So we have yellow, we have yellow, we have colorless, we have colorless. You get the idea. There's a lot of combinations, a lot of issues. So you really have to understand the imperfections in diamond if you want to understand what gives it these amazing and beautiful colors. So this is where we come a little short sometimes, is we don't go beyond that. We don't explain. In order to understand what those defects are doing and why you're getting those colors, you have to understand the light interactions. So this is the electromagnetic spectrum. It spans everything from cosmic rays to radio waves. But the part we care about is just this little sliver, a little bit of the ultraviolet into the violet and the visible, all the way over to the red on the other end of the visible, and a little bit into the infrared. So there's a much more elegant image of this in the previous talk as well. I was quite jealous, but this is basically light coming in, and it's white light going into a diamond when we see it, and that's depicted here. But you got to remember that there are many components of white light, all that blend together to give you that whiteness. When those go into the diamond, they bounce around in whatever ways, depending on how you're analyzing it or looking at it. But what comes out is usually modified, especially in colored diamonds. It's modified in a way that lets you see the color. So you see the full spectrum going in. Here now you see that the entire blue-violet range is missing as it comes out. The diamond absorbed that light, and specifically those wavelengths of light. And that's why we see yellow. This has been known in gemology for a very long time. Bob Crowningshield pioneered work with the spectroscope. And it's looking at the same thing. It's using a prism to actually evaluate the light that's coming out of the diamond after it's illuminated. Now, as scientists, we like a little more detail. So here's the spectroscope image, but now we collect absorption spectra using an instrument similar to this in many cases. And I'll explain what's involved with this on the next. But what I want to point out is you see these peaks that are in this spectrum. They actually correspond to the dark lines that you see in the spectroscope. So it's measuring the same thing. So you've probably seen a lot of absorption spectra, and these are direct measurements of what's causing color in diamonds. So it's really important that you understand what you're looking at. So on the y-axis here, as we go up, we're absorbing more light. And conversely, as we go down, we're transmitting more light. So this red line, this is actually what the diamond is doing. It's absorbing light here, and a little bit here, and not very much here. So we have absorption in this range. And if it likes me. And we have transmission in this range. The only part overlapping the visible spectrum is what comes to your eye. This is the UV visible spectrum of a very beautiful red diamond. But you get the idea. If it's absorbing this light, then all that can get through is here. And that it's critical that you understand that in order to understand these spectra. These are all different. So we have a red, green, yellow, and a brown diamond. And you see the spectra are all very different. They're very similar to the one I just showed you. And this is a 550 nanometer absorption band. This is the primary defect that causes pink to red color in argyle diamonds. The green is colored by radiation-related vacancies. This GR1 is the vacancy defect. And what's interesting is this diamond also has nitrogen absorption. So it's a combination of these two that leave this low area here in the visible spectrum, which is in the green, hence the color. Likewise, defects like N3 and N2, these are the nitrogens around the vacancy. The 3 nitrogens produce these absorptions and give you nice Cape yellow diamonds. And finally, those clusters of vacancies I showed you when I kinked the lattice, those absorb light all the way across the spectrum, increasing toward the blue, and they give this rise, which causes an overall brown color. So I think you can see pretty clearly from these that there's a very big differences here depending on what defects are responsible. So we sorted it all out, right? All the yellow color must come from this. Well, it's not even remotely that easy. Here are 4 yellow diamonds. Canary in the lower corner, Dr. Wang showed you this morning, Cape yellow, I'm just showing you. There are other defects that are responsible for yellow color, and there's several that I haven't shown you here. So understanding what's causing the color requires us to understand the defects that are involved. Some defects, like this N3 defect, the 3 nitrogens around the vacancy, do more than just affect the body color of the diamond. They also do things like this. When you put this light under a 365 nanometer UV or excitation, you get blue fluorescence. And of natural diamond, almost all the natural diamonds that actually fluoresce will fluoresce blue. It's a very useful feature. Being that it's nearly ubiquitous to natural diamond, we can use it in screening tools like you heard about from David earlier in the day. And in general, it has a big effect apparently on the color grading of diamonds. And so these are important things to know, but it's caused by this specific defect, and knowing how much of that is there and that that's the cause is very important. All right, so rarity, I mentioned it at the beginning, and at the end of the day, rarity is really where the value comes from in colored diamonds. I wanted to give you an idea of how rare some of these are. So here are some generic green, blue, red columns. And I want to tell you before I click up any of these numbers that I'm not talking about diamonds that are this green, this blue, or this red. Obviously, those are not common at all. But any diamond that has a color component of green, blue, or red, be it faint all the way up to intense, just to give you an idea of how common they are. So among all diamonds, colored and D to Z, at GIA, combined, these 3 categories account for 0.4%. So green, blue, red is clearly not common. Well, if we go a little further and we just look at colored diamonds, so we get rid of all those no fun, close to perfect diamonds, we look at what has this color component. So the green category, the blue lumped with gray and violet, and then the red with pink, purple, and brown. Still, of all colored diamonds, 10% have green colors, 3 have blue, gray, violet, and 17 have sort of red, pink, purple, brown. That's a big category, I understand. But the idea here, too, is that totals up to about 30%. So that means that pretty much the rest of the colored diamonds, almost 70%, are mostly yellow. So I told you that brown was one of the more common colors. Well, it's not even close to yellow. Yellow covers the vast majority of colored diamonds that we see. And then I even threw in something at the bottom in terms of unmodified hues to even further complicate the matter. These would be greens that aren't bluish green or aren't yellowish green, just that are green. Granted, once again, they couldn't be anywhere from faint to intense. I don't want to confuse that and imply that they all look like this. They don't. But even in that category, the numbers are extremely small. So when a diamond like this, I said nothing about size. I just talked about color. So that also encompassed all size ranges. When a diamond like this rough blue diamond weighing over 29 carats shows up, you can imagine the glee at the mine. They really know that this is a once-in-a-lifetime stone. And this stone was cut into the 12-carat blue moon of Josephine diamond. It's a very well-known diamond that was auctioned a few years ago. And that sort of leads me into the next little bit. So if these diamonds are this rare, and I'll show you how valuable very shortly, people like to treat to the colors. And Dr. Chaim Cohen once again showed us some of these treatments to make some of these rare colors that I showed you. And I have an example, and ironically, this wasn't coordinated, but this is pretty close to how he made his pink to red diamond. Not exactly, but this is a sort of an off-color yellow diamond. It has some pairs of nitrogen atoms in it. If we want to start working with these defects, I mean, we can engineer defects through treatments in order to get different colors. So we'll high pressure, high temperature treat this diamond to start. So what we did is we disaggregated those nitrogen atoms. Something else that Dr. Wang talked about in his early morning talk is whether this occurs naturally or not. Well, we know it occurs in the laboratory. And so now we have single nitrogen atoms, much more color from those single nitrogen atoms because they absorb light differently than the pairs might. Well, we don't need to treat to yellow like this. We can find those naturally. Let's keep going. Now we use an electron beam and we knock some of the atoms out. And I just took out carbon atoms here for the sake of demonstration, but we have vacancies. And those vacancies, they're by themselves. They're not next to these nitrogens right now. So we have yellow color from the nitrogens. We have green color from the vacancies. We have a nice sort of antifreeze yellow-green colored diamond. Once again, that's not what I want. I want one of these really rare red diamonds. So the way I'm going to get that is I now heat this. And I make those vacancies move around. And eventually they run into these single nitrogen atoms. And they create nitrogen vacancy centers. Very different in actual appearance, usually, from the 550 nanometer band I showed you from Argyle. These are another way in which you can make red color and diamond. And it's the only way that you can effectively make red color and diamond through treatment. So I just wanted to show you that to illustrate how these things and why people treat diamonds and how they take advantage of the defect structure. All right, so just a couple slides here at the end. This diamond, this 163 karat D flawless diamond, sold at auction. I think it was near the end of last year. And this is about as good as they come. It sold for a record price for a D flawless diamond. So if you like perfection, then you're probably dealing in 200,000 US dollars per carat, or 0.2 million. Well, I personally prefer imperfection. And because imperfection gives me things like this. And I think you can see the red numbers, they kind of speak for themselves. Sort of capping off here with that blue moon of Josephine diamond that sold for $4 million per carat. And it's only a 12 karat diamond. So the value, the rarity, I think it speaks for itself there. So that's why we care about defects. That's why we care about imperfection not being such a bad thing in diamond. And you know, at GIA, we've looked a lot of these colored diamonds over the years, and we are really making an effort right now to kind of give back to the trade some of that information. And in Gems and Gemology, we're on a mission right now to publish a series of 6 articles that are focusing on different colors of diamond. So a couple of issues ago this year, we did the green diamond article, and there's a lot of information and statistics in there that you've never seen before. The last issue had blue, gray, and violet diamonds. Hopefully we're here within a couple of issues. You'll see pink, red, purple, brown, and we're going to proceed on through the entire range of colored diamonds. So with that, I'll go to my last slide. And I just noticed here there are very few of these perfect colorless diamonds. These are all the nice imperfect ones. So, and thank you. And
thank you very much, Mike. Do we have any questions for our speaker? Yes, please.
It seems, in my experience, in buying fancy colored diamonds versus colorless diamonds, that the clarity grades in fancy colors are much more rarely flawless. Is that just because of what I'm seeing when I'm buying from my particular sources? Or would you say that fancy colored diamonds in general may tend to be more impeded than colorless diamonds?
so I don't know if everyone heard the question. She's observing about the clarity grades on colored diamonds versus colorless diamonds and how they tend to be fewer flawless or internally flawless colored diamonds. I think it's probably more due to the fact that the color is valued more than the clarity in colored diamonds. And so in a colorless diamond, clarity is such a huge price factor. In colored diamonds, not so much. The color so much overrides it that they facet stones with lower clarities because of the value of the color and the rarity of it.
Yes, Dr. Cohen?
I think that one thing that you missed with the red.
Sorry, the mic. Sorry.
Mike, I think that one thing that you miss to interpret, that you never get one kind of imperfection in a diamond. So usually you get 2 or 3 colors which integrate to a color that, you know, for example, when you talk about green treated, this means that you have yellow natural plus the blue. Yellow plus the blue is green, of course, as we all know. When you keep on irradiating and getting more and more blue, and the intensity of the blue is increasing appreciably to much more than that of a little bit of yellow, and then you get the blue color.
I agree.
So, I mean, it's always that you don't get only one kind of color, one kind of imperfection in the diamond, but usually when you try to induce color, you get several colors, and what you get, of course, is the mix of all of them.
You're absolutely right, and that's why I sneak that word simplified in there in the beginning. It gets far too complicated if everything's going on at the same time. But no, going back to the question that you were asking the audience earlier, I mean, it is possible to irradiate to lower doses and make a green color. It's all about that transmission window that I showed you in the spectrum. If you have good nitrogen absorption, you can put a small amount of vacancies in and you can create a green color. But Dr. Cohen's also right. If you increase the dose to the point that you raise the amount of vacancy absorption far above the nitrogen, now your transmission window is, the baseline is raised, but the transmission window is in the blue. So you can make a blue or a green diamond by varying the dose. But likewise, you can make a green diamond with a lower dose if you have the, but I agree, there's definitely a combination of things going on. Nature is not a pretty sight. It's very messy. There's never, none of these are as simple as I laid them out. But the basic concepts are that simple. So.
Yes, sir?
Why is it so difficult to make treated pink diamonds as compared to blues or greens?
I'm sorry, what was the first part? How's it?
Why is it difficult to get treated pink easily?
It's fairly easy to make treated pink, but to make treated pink, you have to have isolated nitrogen to begin because you're making nitrogen vacancy centers. So there are very, very few natural diamonds that are type 1B with isolated nitrogen atoms. You can grow synthetic diamonds and treat them to pink because you can grow them with isolated nitrogen. That being said, the treatment I showed you is one that's come along in the last 10 years, and it's because of that. There wasn't enough of this 1B material naturally to treat to red or to pink, so they started taking more common material that had high nitrogen, breaking up the atoms through HPHT treatment. We call them combination treatments because it requires several. But that's it. That's why pink is harder. The starting material is a little harder to get. And as I understand it, if you want a pure pink or a pure red, you really have to control the initial amount of nitrogen. If you get too much, it turns purple or brown, or too little. Or too little, it becomes orangey. So it's all about controlling that transmission window in the spectrum.
Thank you.
Okay. Let's thank our speakers and let's go out for a break. Thank you.